So today we'll look at representations of functions by power series. And what we're going to look at is sometimes called geometric power series. These are ones where our series is going to look so much like a geometric series, except it'll have an x or an x plus 2, an x minus 1, those kind of things in them, that we're going to use instead of building it by taking derivatives like we did for the Taylor and Maclaurin polynomials. We're instead just going to use the rules for a geometric series. Let me show you what I mean by that. So we're going to start with the simplest one possible. Consider the function f of x is equal to 1 over 1 minus x. Note, that looks a lot like the sum of a convergent geometric series a over 1 minus r, right? It's got x in the place of r. If we let a be equal to 1 and r be equal to x, we have that 1 over 1 minus x is the summation as n goes from 0 to infinity of x to the nth, which is 1 plus x squared plus x cubed, etc., provided that the absolute value of x, because that's r, is less than 1. Right? That's the rule for geometric series, is the absolute value of what you're multiplying by, the common ratio, has to be less than 1. So this is a power series centered at 0. Now, you can actually choose to center this series at any point with differing intervals of convergence. For example, let's say we wanted to obtain the power series centered at x equals -2. There are a couple of things that you have to do. We're going to need to replace this x with x plus 2. When we do that, we have subtracted 2, so that we have to add a 2 on so that it retains its same value, so that these are equivalent. So combining the like terms, then we have 1 over 3 minus x plus 2. And the second thing is that this number needs to be a 1. So we'll divide every term by 3. So they get 1/3 over 1 minus x plus 2 over 3, which is equal to your a over 1 minus r. It's always got to be in that format. So a is 1/3, and r is x plus 2 over 3. So provided that the absolute value of x plus 2 over 3 is less than 1, this is going to converge. And solving that, we get that the absolute value of x plus 2 has got to be less than 3. So again, this is centered at -2. Going 3 to either side gets us to -5 and to 1. And since it's geometric, remember geometrics, we never have to check the endpoints because geometrics always diverge at those endpoints. So let's try this for a different one. We want to find a power series for f of x is equal to 4 over x plus 2 centered at 0. All right. So f of x is equal to 4 over x plus 2. We want it to be in the format a over 1 minus r. So I want it to be minus my x, so I'm going to multiply everything by a negative. So I'll have a -4 over -2 minus x. Next, I want this to be, and this is already centered at x is 0 because don't have anything minus x plus something, x minus whatever. I'm going to divide everything by -2. So this is going to be +2 over 1 minus parentheses x over -2. So now I have it in the correct terms. So this is going to be the summation as n goes from 0 to infinity of 2 times negative x over 2 to the nth power. Notice that that'll give you, when n is 0, the first term will be 2, and then for every subsequent term we'll multiply by negative x over 2. So we want the absolute value of x over negative 2 to be less than 1. Multiplying both sides by 2, we get that the absolute value of the opposite of x needs to be less than 2. Well, the absolute value of the opposite of x is the same thing as the absolute value of x. So my radius of my interval of convergence is from negative 2 to 2. Which we probably on that one at least could have done without all that work. If x over negative 2 has to have an absolute value less than 1, x has to be in between negative 2 and 2. On the AP exam, they're not real big on making you jump through a lot of hoops with these, but you do need to recognize these, because if you can recognize these, it's a lot faster to do this than it is to try and generate it by doing a whole bunch of derivatives. If my memory serves, this one is a little bit uglier. Find a power series for f of x equals 1 over x centered at 1. Okay, so f of x is equal to 1 over x. So we want this to be centered at 1, so we don't want it to be x, we want it to be x minus 1. And we've subtracted 1, so we need to add 1 as well. All right, we want to be subtracting, so we're going to multiply everybody by negative 1. And then we want it to be a over 1 minus r. So I'm going to divide each term by negative 1. So this is going to be 1 over 1 minus x minus 1 over negative 1. So our series will be the summation as n goes from 0 to infinity. A is 1, so we don't have to worry about that. This will just be x minus 1 over negative 1 to the nth power. And since we want the absolute value of r to be less than 1, so we want the absolute value of x minus 1 over negative 1 to be less than 1, well, that means that the absolute value of x minus 1 has to be less than 1. So that means that our radius is 1, centered at 1, so that'll be from 0 to 2. So it's important when you give a power series for something that you also tell its interval of convergence, right? This only converges to 1 over x for values of x between 0 and 2. If you try and figure out, what happens at x equals 3, it isn't going to work. Okay? All right. So since a power series is like an infinite polynomial, you can do a lot of the same things that you can do to a power series that you can do with a polynomial. Namely, you can add, subtract, multiply by a constant multiply series, and even differentiate and integrate. So, for example, let's take a look at this one. Find a power series for f of x which is equal to 3x minus 1, which by partial fractions, I didn't make you jump through that particular hoop, but that could be one of those problems on the AP exam where they're going to go, use partial fractions decomposition to rewrite this, or even to integrate that, okay? And then turn around and go, and now find a power series for it. That's the way on the AP exam, they'll have one stem, but they'll ask completely different topics about the same thing. This would be a good example of one where they could do that. I don't remember them ever having done it, but certainly could. So what we're going to do is write this as two different power series added together and then see if we can simplify the result. So 2 over x plus 1, we want it to be a over 1 minus r, right? So I'm going to multiply everybody by negative 2. Excuse me, by negative 1. And this will be negative 1 minus x. And then I'm going to divide everybody by negative 1. And I know you feel like this is kind of going round and round. And it kind of is. It's 2 over 1 minus the opposite of x. Which is going to be equal to then the summation as n goes from 0 to infinity of 2 times negative x to the nth power where r is the opposite of x. So this is centered at 0. I think you can see that that's going to go from negative 1 to 1, yes? Is that clear, or do I need to show that? Yeah, there was enough of a hesitation. So where we want the absolute value of the opposite x to be less than 1, which means the absolute value of x is less than 1, which then means that this goes from negative 1 to 1. So we have this series for the first part. Then for the second part, 1 over x minus 1, multiplying by negative 1, we get negative 1 over 1 minus x. And that's already exactly in the form that we want. It's an a over 1 minus r. So that'll be the summation as n goes from 0 to infinity of negative 1 times x to the nth power. And here, this is x to the nth, negative x to the nth. It's going to have the same interval of convergence. So negative 1 is less than x is less than 1. So here, f of x is going to be equal to the summation as n goes from 0 to infinity of just the sum of those two parts. So it'll be 2 times negative x to the nth plus negative 1 times x to the nth. I need to put brackets around that because I want all of that to be in my summation. And this will be from negative x, or negative 1's less than x is less than 1. See if we can simplify that a little bit. I'm not sure that we can. I always want to look. So notice I can factor out an x to the nth power. So I'll have x to the nth times 2 times negative 1 to the nth plus, or let's just say minus 1. It feels like you should be able to simplify that some more, but let's see. If n is 0, this is going to be 2 minus 1. And then when n is 1, that'll be negative 2. That'll be negative 2 minus 1. So that's just going to flip-flop back and forth between 1 and negative 3. And there's not a real good way to write that. So it's going to be an alternating series, but a weirdly alternating series. All right. So from our second example, we had that 1 over x is equal to the summation as n goes from 0 to infinity of negative 1 to the nth times x minus 1 to the nth on the interval from 0 to 2 exclusive of both endpoints. They want us to use that to find a power series for natural log of x also centered at 1. Like, okay, well, how is natural log of x related to 1 over x? What's the derivative? There's two it's there.
The 1 over x is the derivative.
Yeah, 1 over x is the derivative of natural log of x. So if we're starting with 1 over x, what do we need to do to find natural log of x?
Integral.
Yeah, I need to do the integral. So natural log of x is equal to the integral of 1 over x dx. So this is going to be the integral of our summation as n goes from 0 to infinity of negative 1 times x minus 1 to the nth power dx. So that's going to be the summation as n goes from 0 to infinity of, we keep the negative 1 to the n because that's constant. We'll add 1 to the power and then divide by that new power. We should also think about plus some constant, right? Because we're taking the antiderivative. You're like, okay, I don't really want to test this very much, so I'm going to let x be equal to 1 because I know the natural log of 1 is 0. So at x equals 1, I'm going to have the natural log of 1 is equal to the summation as n goes from 0 to infinity of negative 1 to the nth. I'll have 1 minus 1 to the n plus 1 over n plus 1 all plus c. Well, natural log of 1 is 0, and every single term of this series is also 0. So C is equal to 0. That's going to happen a lot of the times, but you always need to think about, all right, well, what is the constant here so that I can make these two equal? So that means that natural log of x is equal to the summation as n goes from 0 to infinity of -1 to the nth times x minus 1 to the n plus 1 over n plus 1. We know that this went from 0 to 2. I know that it cannot converge at x equals 0 because natural log of 0 doesn't exist. If we think real quickly about what happens at x equals 2, at x is 2, this is going to be 1 to the n plus 1, which will just be 1. So I have -1 to the nth over n plus 1, which is a converging alternating series. So it will include 2. This is one of the ways that we can find a series for something that we're interested in. All right, so here, let's find a power series for f of x is equal to arctangent of x. You're like, arctangent of x. Well, remember that the integral of 1 over 1 plus x squared is equal to dx is equal to the arctangent of x plus some constant. So I'm going to start by finding a series for 1 over 1 plus x squared. Again, I want it to be a over 1 minus r. So I'm going to multiply everybody by -1. And then divide everything by -1. So this will be the opposite of x squared. And you can skip over this second step if you want. I just find sometimes if I do too many things at once, I get lost. But yeah, this is be 1 minus the opposite of x squared. So this should be the summation as n goes from 0 to infinity of a, which is 1, times r, -x squared, to the nth power. And then we want the absolute value of the opposite of x squared to be less than 1. Which means that, I'm not going to take the time to do this entirely, but I think you can see pretty quickly, which means that -1 is less than x is less than 1. So now that we have a series for 1 over 1 plus x squared, then arctangent should be c plus, and I'm simply going to take this series for arctangent and take the antiderivative. So the summation is n goes from 0 to infinity of and I'm going to rewrite that as this is -x to the 2n. So it'd be -x to the 2n over 2n plus 1. Oh, sorry, negative x to the 2n plus 1 over 2n plus 1. And I believe it has the same interval of convergence.
And you don't have to find C?
When x is equal to 0, arctangent is 0.
Oh, okay. I see.
So C ends up being 0 again.